Cool. So this is great. I love that fact that we're asking questions and commenting. Again, feel free to unmute yourself and speak out loud as well. I'd love that. So taking a step back, where are we so far? We've spent about close to one hour, 15 minutes on this. And hopefully I've tried to convince you that marketplace and recommendations in the marketplace is a multi-stakeholder problem. We have different stakeholder and objectives. We're now going to look at some of these methods in which we can look at some of these objectives. And then we're going to go and look at some follow-up later on. So the summary of the first part was that traditional reg search systems are mostly user-centric, and we should consider multiple objectives, and we should devise ML models to optimize those objectives. In the second part of the tutorial, we looked at different case studies, like 7 case studies, and then we looked at like what some of those objectives could be. But very interestingly, that analysis at least got us started to think that, oh, I'm dealing with these objectives. Some of these are helping, some of these are hurting, some of these are neutral. So now we have a sense of what are we dealing with when we go into the method section. So again, like we need these ML methods to model the interplay between objectives. And it's very important to carefully decide what a system optimizes for. So yeah, so this leads us to the third part of the chat of this tutorial, which is like methods for multi-objective ranking and recommendations. So we're going to define the notion of Pareto optimality, and then look at a few specific classes of problems. We're going to start by looking at multitask learning, then look at scalarization, come back and look at multi-objective bandits and multi-objective reinforcement learning. So we're going to look at a few of these multitask learning approaches, not just one. We're going to look at a few of these reinforcement learning approaches, not just one. So again, we're going to look at 4 different broad categories of models. And the reason for us to do that is so that as a system designer, you can make an informed choice on what kind of solution you want to deploy. So it depends a lot on the maturity of your infrastructure, that maybe a scalarization approach is the best first solution, or maybe we have milked away all we could from some of these low-hanging fruits, and I really need to deploy an online RL model for my use case. So again, we're going to walk through some of these and then keep on discussing on where we might want to use them. So let's start by talking about Pareto optimality. So this, I'm pretty sure a lot of you are familiar with this. Pareto optimality is an economic state where the resources cannot be reallocated to make one individual better off without making at least one individual worse off. So Pareto optimality is not just one solution. It's a sense of all the solutions wherein everybody is at the peak of where they could. And if you increase somebody even further, you're going to hurt at least one other person. So an example here is in a Pareto optimality sense, it kind of implies that the resources are allocated in the most economically efficient manner. So again, like if you look at the plot on the bottom right, then the red colored points are Pareto optimal solution. Like if you have to increase a solution for any one objective, then you have to decrease it for the other objective. And all of these solutions lie on the Pareto front. And it's very important to note that Pareto optimality does not imply equality or fairness at all. Because again, like it does not say that everybody gets the equal weight or equal exposure or anything like that. But it's just that like, it's just a state wherein you cannot make one better without hurting another one. So again, like the Pareto frontier is a set of parameterizations or allocations that are all Pareto efficient. So this is very interesting because ideally, as a system designer, I would love to just walk on the Pareto optimal front. I mean, if I'm the product manager making decisions on, or an engineering manager making decisions on what my product is doing, then ideally, I would love to just stay on the red curve and then make decisions based on what I want to do. So as long as we are on the Pareto frontier, then we can ensure that I have the best possible solution. And then which among these should I decide is based on what objective should I give more importance to. So again, the Pareto frontier enables making focused trade-off within the constraint set of parameters we have. If we want to focus more on objective 1, we can go all the way to solution H. If you want to focus more on objective A, we can go, if you want to focus on objective 2, we can go all the way to solution A. So with that understanding, again, why do we need that understanding? We need that understanding to kind of understand that we have multiple solutions on offer. And each time we're picking a solution, we are making an informed choice that I'm going to trade off satisfaction for supplier metric, or I'm going to trade off revenue for satisfaction metric. So these are all informed choices which we need to make and which our models should allow us to make. So with that background, we're going to look at some of these approaches to multi-objective methods. Before I go into some of these specific approaches, I want to give a broader perspective on how we should be thinking about some of these methods. So first, we can look at some of these multi-objective methods in a multitask learning setup. That, okay, I want to consider multiple objectives, but most of the objectives I have are predicted outcomes. So then I'm not making one prediction, I'm making multiple predictions. So that is more of a multitask learning setup. That when a user comes in, I care about the user streaming something on the platform, user returning back to the platform, user becoming a fan of the artist. So these are all prediction targets which I have to consider. So I can develop a multitask model solution to get me these multiple objectives. Now, once we have these multiple objectives, then we can think about aggregating these things. So again, once you have multiple objectives, now you have to make a choice on how do we kind of interact with these multiple objectives and devise solutions in a multi-objective way. So some of these solutions could be scalarization-based solution, or we could do it together, that I have a multi-objective, multitask learning system. So I'm predicting multiple things, but I'm doing it in a multi-objective way. Or I want to be very online in my approach, that I want to make predictions in real time and use them in a bandit style setting to decide what we do next. So again, so this is the classes of solutions which we're going to discuss. Just a quick recap. We're going to start with multitask learning and say that, hey, at real time, you can make multiple predictions, which you can then use to combine things in a scalarization or other way, or you can do things combined together. And that is the 4 different classes of methods we're going to look at. So you're going to start with multitask learning and then go on to scalarization and talk about bandits and multi-objective RL next. Okay, so multitask learning. So multitask learning is pretty well known so far in the sense that like it's been fairly commonly used in a number of different domain areas, like including computer vision, NLP, recommendation problems, search, ranking as well. So multitask learning leverages useful information, which is contained in multiple tasks, and it is used to help improve the generalization across multiple tasks. So an example here could be that I have a neural network which has 2 shared layers, all the parameters are shared, and then I have task-specific layers. So this is a very concrete example of hard parameter sharing, that no matter what, the parameters for the first 2 layers are going to be the same for both the task 1 and task 2. So task 1 and task 2 could be predicting whether the user is going to become a fan of this content, or whether the user is going to come back, or whether the user is going to save a playlist or not. We can also do some soft parameter sharing. So instead of a hard parameter sharing saying that, hey, it's going to be the shared layers, all the parameters same, we can also enforce this in terms of making the weights of the layers similar to each other. So here we say that I have a loss function which considers the loss on task 1, loss on task 2, but also I want to ensure that the Frobenius norm between the weights of these layers is low. So what that would say is it will try that regularization term will try to make the weights across these 2 tasks and the bottom layers consistent and close to each other. Now, this is just a beginning, right? I mean, a lot of work has gone into designing a lot more sophisticated and more nuanced multitask architectures. So there's a very nice paper from Sebastian Ruder at AAAI 2019, which talks about latent multitask architecture learning. So if you look at the example before, here we were very concrete and hard in the sense of there's going to be either hard parameter sharing or soft parameter sharing. In this example of fluid networks, the system is trying to learn what to share between loosely related tasks. So again, let's dive deeper into this. So we have a shared input layer. So that means the input is the same. And at the end, we have a task-specific output layer, very similar to the first examples we saw. But what happens next is very different. So here, the parameters inside the Sluice network gives us a way to control the sharing between the tasks. Now, the motivation behind looking into something like this is that often we don't know how relevant some of these tasks are with each other. So when we don't know how relevant they are, then we better let the network decide on how much you want to share. Is your task one really helping task two, or is your task one really like saying something completely different than task two? So instead of making these choices manually at the start, we want to defer it to the model to see that, okay, are the tasks related? And if they are, then I'll let my parameters decide on how do I want to share information from tasks between tasks. So looking a bit more detailed into this, so if you see that between the two parallel layers, we have some of these alpha parameter boxes. So they enable adaptive sharing. So essentially, the flow of information between tasks is mediated based on the parameters alpha here. So these are parameters of the model. So based on the task, based on the pair of tasks at hand, the architecture decides whether we want to share these parameters, whether we want to transfer information from one task to the other or not. And interestingly, there is also this inductive bias term added. And this is very important because we don't want both of these like parallel architectures to like, or both these layers to learn the exact same thing for the two tasks, right? I mean, we want to encourage a division of labor. So essentially what this inductive bias terms does is it adds a penalty to enforce a division of labor, and it discourages redundancy between the shared and the task-specific architectures. So again, if we zoom in into some of these red box a bit more, then we see that I'm going to pick up this example here. I hope you can see my mouse, which let me see if I can annotate. Nope. Mouse, yeah. Okay, yeah. So if you see my mouse, then you can see that each of these layer is divided into two parts. So one is a shared component of that layer, and the other one is a task-specific component of that layer. So essentially what happens is that at each layer, we have divided it into a task-specific and a shared component. Now, essentially what we want to do is we want to say that I want both these parts not to learn the same thing. I mean, I want them to do different jobs. So essentially adding this inductive biases helps to say that, hey, this GA21 and GA22 are going to do different things for me. So essentially, this kind of discourages redundancy between the two subcomponents of the specific layer. So again, what's happening here? I mean, just taking a step back, we saw that we could either do a hard parameter sharing or do a soft parameter sharing, or we just let the network decide that based on the task you have, do parameter sharing based on however you feel is better by adding up adaptive sharing parameters and adding an inductive bias system. So how do I get rid of that? Yeah, okay. So beyond that, I mean, this is just one of those examples. I'm going to briefly touch upon a few more examples and then head over to the first break. So again, like there is some work at CVPR 2016 looking at cross-stitch networks. So this is another formulation of information sharing, wherein you have two networks and there's a cross-stitching between these networks, which modulates how much information you're sharing between one and the other. There is also this, like in the NLP domain, there's a joint many task model. So again, you're not just doing a 2 task, 3 task, but you're doing like multiple tasks like entailment, chunking, power speech tagging, and all of that together. Again, like huge advances have been made in the NLP community, which leverage these multitask architectures very nicely. There's very nice work around using uncertainty to weight losses. So if you pardon me, I'm going back a few slides. If you look at these two equations here, so we always have to decide on how am I weighing my losses. So either I can define these lambda parameters manually or obtain them in some way. So this CVPR paper, which this CVPR paper says that we can use uncertainty about the task to decide the weights for the different losses. So when we are training a multitask model, then I'll let the different task specific uncertainty decide what the weights should be when we combine losses from multiple tasks. And also there's some very nice work around hierarchical tasks. So again, the tasks need not be all at the same level. You can have some base tasks like entity mention detection and named entity detection. And then you can use the learned network from there for task higher level at the hierarchy. So like co-reference resolution, relation extraction can use insights from the base task as well. So if you see, like you can see these additional short circuit networks. So there is a short circuit from directly here, which goes all the way to the hierarchy of task. So this is important. I mean, we've been experimenting with some of this internally at Spotify, and we've realized, at least in the experiments I've been running, that if you don't add these short circuit networks, then things get lost. I mean, again, if you take an example, then let's say this is task one, like the name entity recognition task. The error of task one modifies the encoder here. And then the error from task two modifies the encoder here. So by the time we go to some of these hierarchical tasks, then the task specific encoders have been polluted enough by task at the lower level. And that's why, I mean, we rarely see changes in this coming up. So essentially, to counteract that, one way would be to short circuit it and say that, hey, I'm going to allow you to pass information from these layers, but also I'm going to short circuit and directly add a link from one of my base layers to one of these hierarchical layers. So I think this is a very nice trick to kind of short circuit some of the steps in between and pass on information down the road. So again, nice architectures around multitask learning. So quickly going into, I'm going to take another 5 minutes before we go into the break, because then, yeah, then I'll take a few questions and then go into a half an hour break for the second part. Okay, so what we've done so far is, we've said that, hey, you can make multiple predictions, because I alluded to the fact previously that when you're making some of these objectives, then some of these could be predicted. And if multiple of these are predicted, then you can use some of your multitask networks to predict multiple things. Now, what do you do when you predict them? You try to now combine it, right? So once you have multiple objectives, an easy first solution around multi-objective methods could just be scalarization. Scalarization is just a fancy term for aggregation, that I want to aggregate information from multiple objectives together into a single score. So let's consider two objectives, like relevance. I gave this example slightly before as well, when we were saying that do playlists have relevance and fairness as well? So let's go back to that example. And here we want to consider two objectives, like the user-centric relevance and supplier-centric fairness, or fairness or diversity. So what could we do? I mean, how do we balance these two objectives? Very simple solutions. I can disregard fairness and only consider optimizing for relevance, or I can only consider optimizing for fairness and disregard the other objective. I can do a probabilistic policy that I'm going to flip a coin, could be a biased coin or a fair coin. You can parameterize a coin flip as well based on how often you want one to be picked over other. And here I can make a probabilistic decision that I'm going to maximize my relevance for some of these sessions, or I'm going to maximize for fairness for some of my other sessions. But here you are necessarily making a decision that that you're only optimizing for one objective in each session. I think this is a nice way to look at the problem, that in aggregate on a global scale, I don't want to do a multi-objective problem for each session. Instead, what I want to do is, like, I want to treat each session as a single objective problem, but I'm going to change the objective in different sessions. So essentially, I could pick up some users and only optimize them for relevance. And I could pick up some other users' sessions and only optimize them for fairness. So there, you're solving necessarily two single objective problems, but you're doing it in parallel across sessions. So that gives you that flavor of multi-objective modeling. Or we can, I mean, instead do multi-objective, very naive multi-objective in each session. So in each session, I'm going to consider both the relevance and the fairness scores, and then combine them in some way. And this combination, this naive combination, is the simplest way of aggregation, right? So aggregation is just very easily an average function is an aggregation. A weighted sum is an aggregation function. But this is not enough. Aggregation is a very rich field in and of itself. And I would like to encourage you to kind of go and look beyond simple weighted averaging. And we're starting to see some gains internally as well on some of these methods. So again, an aggregation is just a function, which is a non-decreasing function, which allows each vector to receive a scalar value to be optimized. So essentially what you're doing is you're picking up a bunch of values and then you're quantifying them to get just one output from them. So we know min, max, weighted sum, some are very simple forms of averages, but some of these other like more nuanced forms of averages like ordered weighted average, OWA. So these are very rich mathematical structure. So an ordered weighted average literally says that, hey, I'm not going to just do an average, but first of all, I'm going to order my scores based on some property, and then I'm going to decide what weight to give to them. So there are ways in which you can parameterize these OWA functions. So in the weighted sum, you're saying that I'm going to pre-specify the weights at the start, and then I'm just going to do a weighted sum always. In ordered weighted averages, there is a mathematical way in which you can say, hey, I'm not going to fix my weights. I'm going to let the model pick up these weights based on the scores which some of your objectives obtain. So I think this is a very rich mathematical structures which we're kind of recently exploring in a lot more detail. So I encourage you to kind of go and have a look at some of these. So yeah, so I'm just going to pause here for a bit and just give a trailer of where we are and where we are headed to. So what we have done so far is we have looked at the introductions to marketplaces. We looked at some optimization targets. We've recently looked at multitask learning and how do we combine things, and a bit beyond simple weighted averaging as well. What I'm going to talk about next is multi-objective multitask learning. So here, this is a very nice recent papers at NeurIPS 2018 and 2019, wherein they treat the multitask learning problem as a multi-objective optimization problem. And then they try to solve this in a nice online fashion. Once we're done with that, we're going to look at multi-objective bandits and some of these RL approaches. Finally, after that, we're going to spend half an hour on some recent research which shows that you can leverage some of these consumer and supply understanding to kind of benefit some of your core models. So we're going to take a half an hour break now and then come back at time is it? Right, so we're going to come back at around 10:15. Let me see, check the time. Yeah, so we're going to come back at like 10:10 essentially, and then resume. And I'm going to answer. I'm going to answer some of the questions in the meantime. And we're going to see everyone here at like 10:10 again. I'm going to just keep the slide open. Okay, I'm going to take a couple of questions. So so there's so the afternoon session is the second part of the tutorial, which is on automated recommender systems. So essentially, like this is not really linked to the first part. And the second part essentially is like almost completely different in the sense that they're all related to the advancements in recommendation systems. But then in the first part of the tutorial until under 12, we're talking about marketplaces and multi-stakeholder platforms. In the second part of the tutorial, there's another set of tutors who are going to talk about automated recommendation systems. So the website has a bunch of details around that as well. Okay, I'm going to come back after the break to address some of the questions. So please feel free to write more during the break. And I'll see you guys in 25 minutes.